I'm still munching on a little snack here, and I'm just going to go over what we're calling this stream. This Raudive diode thing. It has to do with picking up audio energies from the outside world, much like a crystal radio. Let me just find my stream, and I want to go over kind of what like a summary of what I've discussed all evening about the stuff that I'm going to be building, and I think that would be the near future, like within the next, let's say, 7 days. We'll build this stuff. We'll work on trying to. I gotta find some wire to build this antenna or something. I don't know, but anyway, I'm still kind of working on the snack. There was one video that I had left. I wonder if it's on that we didn't get to finish to watch. I don't. Where did I do? Let's see if I can find that video. Is it on here? I think it's this one. I'm still working on a snack, so we'll listen to this video here. It has to do with we were talking about the RF choke, and I never got to finish this video because I got so sidetracked. And then that got us into the gyrator thing, which got us into the VLF receiver, and we're going to go into that in a minute, but I just want to watch this. We're talking about bypass capacitor and that sort of thing.
Considerably different situation, abbreviated RFC. So that is an example of an inductor in a choke application. Now suppose we have, on the other hand, a considerably different situation. We have a receiver input, tuned circuit here, variable capacitor and coil to provide the frequency that we might want to tune this thing to. Suppose we just want to hear that same 7 megahertz signal, and we have this thing tuned to that frequency. We have our antenna, and we have a coil that goes straight to ground. Well, we have this capacitor here in order to float the antenna above DC ground. But suppose we don't want to do that. Suppose that we are skittish, as it were, about that maybe this is a very long short wave receiving antenna, long random wires, say 1,000 feet. That's going to develop a pretty significant electrostatic charge, which can become dangerous. Even on a clear day that can happen, but if thunder showers are anywhere near, we get a huge voltage on here, and that can be quite dangerous. So what do? Well, one thing we might do in a situation like this is to get rid of this capacitor and just connect the antenna straight to the coil and let this coil short it to ground, so that that will keep the antenna at DC ground potential while still allowing the signal to get on through. So in that case, this coil right here is serving as a shunt inductor. Well, suppose that that is a very small light duty coil, and we're a little bit on the nervous side about having that possible current, which might become considerable in the event of a nearby thunder shower. That could fry this little coil in a receiver like that. Those coils are oftentimes pretty small affairs. Well, we put that capacitor back, and this is a big capacitor, by the way, maybe can withstand 600 volts, maybe even an air variable set to maximum capacitance, something like that, to protect this coil against that current. But we don't want that charge building up on there. So what can we do? We can wind a very heavy duty coil here and ground it directly to the earth. That would be a powdered iron core coil. Another radio frequency choke in effect, but it would serve also to shunt that discharge to ground. So in this case, we could consider it as a shunt inductor. So that is just an example of how we can use inductors, in one case for the purpose of choking something off, that is, keeping the radio frequency energy out of the power supply, and on the other hand, shorting something out, in this case shorting out the DC. So this is in effect a DC shunt. Stan Jabalisco signing off. Until next time, so long.
An inductor is a coil of wire wrapped around a magnetic material.
By who?
An inductor is a coil of wire do not like to change. As a result, an inductor is a device which tries to prevent the current flowing through it from changing. If the amount of current flowing through the inductor is constant, the inductor will be happy and it will not generate any forces on the charged particles flowing through it. In this case, the inductor behaves just like a normal wire. On the other hand, if we try to interrupt the current flowing through the inductor will generate a force, trying to keep the current flowing through it. If an inductor is connected to itself, and there is no resistance in the circuit, the current will theoretically continue circulating forever. However, unless we are using superconductors, all wires have some resistance to them, and the current will eventually decay to zero. The larger the resistance, the faster the current will decay. But the larger the inductance of the inductor, the slower the current will decay.
This is a little slow. Speaking of slow.
Once the current is at zero, the inductor will want to keep the current at zero, due to the fact that an inductor tries to prevent the current flowing through it from changing.
Hello, and welcome to this section of the Circuit Analysis Tutor. In this section, we're going to talk about the circuit element called the inductor. So we'll talk about what an inductor is, why it's important, how does it compare to what we've learned in the past, and then in the next several sections, we will have some basic circuits that we'll begin to analyze that will have inductors in them, and you'll get some experience with trying to understand and predict what's going to happen when you have inductors in circuits. After that, we're going to talk about a capacitor, the circuit element that we called capacitors, and we'll do the same kind of thing. We'll talk about why it's important, why it's useful, some basic circuits with capacitors, and then as we march down the course, meaning this set of lessons and the lessons that follow in volumes to come, capacitors and inductors will be in almost every single circuit. There is not a single circuit that you could open up in your house, television, phone, video camera, anything. There's not a single circuit that you could open up in your house and look in there and not find a capacitor. There's very few that you could open up and not find an inductor. They're absolutely central, critical circuit elements to shape and cause the circuit to do what we want it to do. All right, so before we get there, let's kind of back the truck up a little bit, do a little bit of a synopsis verbally of what we've covered to this point in the circuit classes that we've done so far, because ultimately it's taught this way for a reason, okay? So what we did is we first started talking about what is voltage, what is current, what is resistance. Those are fundamental things that if we have something called inductor, right? The symbol for an inductor in a circuit is very simple. So it goes like this, and you kind of see like a coil of wire, like a little well, what's going on here is you have a wire and you have it coiled. So if I send current, electric current, down this wire, what's going to happen is the current's going to go, and then it's going to start going through the coil, right? Because it's one continuous piece of wire that's coiled up on it like a spring. So the current is going to go round and round and round and round and round. Maybe this coil, I have 4 coils there, but in a real inductor there might be a 100 turns or 75 turns, right? The more turns basically is going to concentrate the magnetic field inside of this hollow region inside of there. Right? Now the reason why it concentrates magnetic field I could teach you, but it's not really the point of this class to teach you the physics there. But if you look at the magnetic field on a wire and you look at the geometry of a coil, then when you run electric current down there and you do the physics, then inside of that coil the magnetic field is going to be concentrated inside of this coil. Right? So it's going to kind of go, it's like a donut, but it's strongest inside of this coil. They're kind of like peanut butter and jelly, right? They're cousins, right? They operate in a circuit with slightly different fields, but their purpose is to store energy, right? So you can build complicated circuits that use these phenomena to do what you want, like transmit radio waves or operate a microwave oven or whatever, because you're trying to deal with handling energy in those circuits. All right. So we've talked about the symbol for an inductor. We've described what an inductor would look like. We've talked about the fact that it stores energy in a magnetic field. Now it's time to look at what an inductor might look like from the point of view of circuit analysis. Right? So let me go and draw a little line here. I'm going to write down an incredibly important equation on the board, and I want you, to not be too scared of it, but we're going to learn from it. So let me go and write this inductor down again. Okay, I'm just going to write the same inductor down. So here is inductor, coil of wire.
The number of turns, the length,
now,
the width.
Now this inductor, we're going to call
area,
it
cross-sectional area,
inductance L, which could be 10 millihenries, 20 millihenries, whatever. All right.
Determine
so
values.
Much like resistors, right? We might send a current down this inductor. Now, when I draw it like this, what I mean is it's going through the coil over, round and round and round, then it comes out the other side. That's what that means. But let's say we send a current I down this inductor. Now, much like resistors, you might expect there to be a voltage across that inductor, right? Remember Ohm's law? We talked about Ohm's law before. If you have a resistor, you're sending a current down there, there has to be a voltage across it, and we use the passive sign convention. The direction of the current flow, we have a voltage drop, plus to minus, right? If you just make a resistor here, this drawing is something we've covered many times before. When you have the passive sign convention, you have current going, you should have a voltage drop across your circuit element. So that's the sign convention for an inductor. When you have current going through it, you should have a voltage drop across it. But the major catch, the major difference, the thing that makes you scratch your head is if it were a resistor, I'll just write this here, if it were a resistor, if it were a resistor,
it would have a DC voltage.
Then what you would have is V is equal to IR, where R is the resistance. Of course, we don't have any R here. We have inductance, L, which actually I forgot to tell you. The unit of inductance is a Henry, but we refer to, instead of R for resistance, we refer to it as L, right? So for L, it means inductor. And by the way, you use L because, it's an inductor, so you think you might call I, I inductance or whatever, but I is current, so you really can't use I. So we use a different letter. C is going to be for capacitor, R is going to be for resistor, L is going to be for inductance. I know it's a little weird, but we just have to do that because we can't use I.
No, it's not weird.
But anyway, if this were a resistor, you would have V is equal to IR like this. But this is not a resistor. So we're going to kind of X through this, right? And what you really want to know, or what you really want to memorize, is that the voltage across this inductor is equal to its inductance L times the derivative of the current with respect to time.
L di dt.
And I'm going to circle this because really this equation here is really the point of this entire section, to explain to you that
That's
the voltage across the inductor is
divided by the change in
LDIdt.
time.
So repeat this with me a few times. I had to do it when I learned circuits. It really does help. V is LDIdt. Voltage is LDIdt. V is LDIdt. So say that over and over again.
No, I don't have to
so when
say
you're
it
talking
over and
about
over.
inductors, it's not current times resistance. There's no resistance here. We haven't discussed the concept of resistance in terms of inductors, but we have talked about the concept of inductance. The more coils of wire, the higher the inductance value, the more it stores magnetic field.
That means it's an
Right?
AC value.
This voltage here is equal to, or proportional to, or equal to, the value of the inductance times the IDT. Now, for those of you who have calculus under your belt, you know that this means the derivative of the current I with respect to time. For those of you who haven't had much calculus or don't remember any calculus, that's okay. I'm going to explain to you what this means. Basically, what this means is how fast the current I changes through the inductor L, right? So what this means is that, all right, what this means is that if I have a inductor with a value of so many henries or so many millihenries, okay, and I put a current through it, let's say, right? And that current is steadily increasing. In other words, I have a knob on my meter and I increase it, increase it, increase it, increase it, increase it. I'm increasing the current, right? That means that didt, the derivative or the change of current with respect to time, is a constant because it's constantly increasing. Then I'll have a number for the rate of change of that current times the inductance. That is the voltage across that inductor. So if I actually go in the lab, put an inductor on in a circuit, hook a current source up to it, and then slowly increase the current where I'm changing the current constantly at a certain rate. That's didt,
That's not me,
right?
by the way.
And then I multiply that rate
this is some other
times the
guy
inductance.
talking.
Then I'm going to have a voltage across that inductor that I can measure with a voltmeter. I can
Make
put
that
the probes
point.
across and see that it's so many millivolts or whatever, right? But it's proportional to the rate of change. It's not proportional to the current. It's not that the voltage is proportional to the current. You have to get that out of your head. It's not proportional to how many amps is flowing through it. I could have 100 million amps flowing through this inductor, but no voltage, right? Because it's not proportional to the current. It's proportional to how fast the current changes, right? How fast the current changes. To put this in perspective again, let's say I put 10 amps through this inductor. 10 amps, that's a lot of current. That current could kill you, right? But let's say I don't change the current. It's a constant 10 amps. So I have a breadboard here, or a circuit, and I have an inductor. I hook a current source and I send 10 amps through it. But I don't change it. It's a constant 10 amps. The 10 amps is constantly flowing around and around and around and around and around. Well, even though it's 10 amps, the rate of change of that current, how fast the current is changing, is zero. If I put a constant current, whether it's a constant 1 amp or a constant 5 amps or a constant 10 amps or a constant 100 amps or whatever, if it's not changing, then didt is zero. So that means 0 times anything is 0. So anytime I have a current flowing through an inductor...
So as you remember in the other previous video, the input to that Raudive diode, that circuit acts as a current source. So, and it's going to be a variable current source, maybe or maybe not. So possibly we can use a Tory coil in there. I don't know, we have to figure some stuff out there.
Right? That's not changing. It's not going up and down or changing or increasing or decreasing or whatever. If it's just constant. Like if I hook a 9-volt battery up to an inductor,
this guy is
right? There's going to be current flowing. To show you how this works and to kind of solidify it, but I'm kind of doing a lot of talking here because this kind of concept's voltage.
All right, so anyway, let's just drop that. Let's go to, oh yeah, wait, did I? It's ITC, that's YouTube. It's just going through the threads on itcbridge.com. There's another diode circuit. Here's an attached image. I want to save that image, so we'll just wait a minute here. That goes in documents. I don't know what that image is. That should be not video, but oh, these are different diode, Raudive diode things that this guy was working on. Now, I don't know why he says 300 to 350 kilohertz. That's incorrect. Now, see, this is starting to look more like. See here, the diodes between this inductor and this capacitor, whatever. The diode. It's not the original Raudive diode design, whereas the one on the far right is. I don't know exactly what he's doing there. From my experience, the Raudive diode is now relatively non-resonant to a wide figure raised broadcast, therefore allowing it to be more broadcasting noise, so much voice can be formed. A noise generator. Antenna must be kept very short. The antenna is meant to be kept very short and adjusted in length so noise just becomes audible. Oh, this is interesting. The Raudive diode. As such, it is essentially a noise source generator that provides raw energy for the voice formation process. The antenna is meant to be kept very short and adjusted in length so noise just becomes audible, but no longer, so that radio station voices are not being received. If resonance was desired in the design, as on a crystal radio, the original broadband functionality could be synthesized by choosing it to be self-resonant in an unused part of the radio spectrum, say below the long wave, etc., where atmospheric noise is quite high and no radio traffic is present. So that's an interesting concept, where I was thinking about building in their VLF radio to build the main antenna to see if we could, to see how sensitive we can make our circuitry. But then we might have too much noise coming into the circuit. In other words, it would be too hot. So then if we cooled the circuit, we could even bring the noise down even further. That's pretty interesting. Here it says, now this guy's arguing, Raudive diode was thought to be a broadband noise source, but I see it's not a source, but it's a receiver. It don't produce noise it receive. 3-inch recommended copper wire, and I heard a radio station. I used a coil with a ferrite core. Well, that's a problem right there, because he's resonating at a certain frequency. And try to tune 350. Use of the ferrite rod may not be a good idea to its high Q and sensitivity. An RF choke of equivalent or higher inductance value, so the Q and radio pickup ability is much lower. Also put a resistor across the choke to lower the Q even further. Try 10K to start and then lower the values to get the Q down. The idea is to receive atmospheric noise without receiving radio stations. So you want to make it resonant. So if you want to make it resonant, it needs to be in a band that's not used for radio broadcasting. And then this guy, moderator, says, I would encourage you to move away from the idea of radio. It matters not which frequency it is tuned to. All it matters is that it does produce noise. It may be the germanium itself, and that is the key. There's a chat here, if that's available. The Raudive diodes do not produce noise. I don't understand. You say it not produce anything. It's only a receiver. That's incorrect. The diode itself may not produce noise, but the crystal detector, if you move it around, does produce noise, and diodes do actually produce noise. In fact, if we look up diodes are actually used as noise sources. So that guy does not know what he's talking about. Here's a Zener-based noise source. A noise generator is a circuit which produces electrical noise. Noise generators are used to test signals for measuring noise figure, etc. and generating random numbers. That's a Zener diode with a resistor. I don't know what UN is. There's all different kinds of noise. We're not going to get into all of that. But I just wanted to point that out. No, that address is not available. That whole website's not even there. When you add an amplifier to the output of the Raudive circuit, that amplifier within here amplifies the noise that the circuit's receiving. It does receive because it is sensitive to radio waves. It is these radio waves that go on to produce the noise required for EVP type communications. That's the right idea. It's a little backwards, but damn it, why can't I open this? Bear with me. Oh my god. What the hell did I just do? I think I did something wrong. Bear with me. I'm moving a file. I just don't want I'm gonna look at this in a minute here. Coldest. And go back to something here. Voice recipient cold dust method and electrical linked up diode. I've saved this file. The cold dust cell. The voices received with the carbon rod method are rarely quietly welded modulated voices, more frequently loud whispering voices, and hug fixed to a loud encapsulated voices to which must come to your ears. That's a battery, a variable resistor. Another variable resistor. I don't know what X and Y is. coal dust cell, which has a crystal detector still from the grandfather time of the radio. One gets coal dust by files of a carbon rod from a slaughtered 1.5 volt truck and battery. It does not have an old crystal detector, which can be used to solve a problem differently. One takes a dry bottle cork. If one cuts strong disc to 3 off with sharp meter, one excavates another larger piece of cork out in the way. A pin is won by scooping out in such a way. The pin is covered. With electric 3 further pins are now needed. 2 of the pins serve as a disc, and the under is such an attachment. What is that, a coil? Looks like a coil. I didn't know. Intoxication-rich diode. I have no idea what this is. Galena. It's galena pyrite salt. Strange. There's some pictures. Attached image. I am indicating the coil as such. That's an RFC choke. For the Raudive design, if you want to use a low frequency that is free of radio traffic, I'd use the 4.7 millihenry choke like this one. Wow, that's got a lot of windings on it. Another better option is to use the higher Q coil and make it a tuned frequency. I don't know why they're... That's not there. Ew, what was that? Map one. It's better to use a non-radio type of noise source. Well, my question is still without answer. This A1997 is having problems. He doesn't really understand. Here's the second picture. The self-resonant formula is F equals such and such. That's not a resonant, well, LC. When L is the self-inductance, C is the parasitic capacitance. Oh, they're talking about... Yeah, but that's... I made calculations, and the 0.5 millihenry produce AF between 300 and 350 kilohertz. And they're talking about... Yeah, but that coil is not even in there. You don't even want that. The coil is not in that Raudive diode. Unless if I'm missing something. Here's the book I used. Cosmic microwave background radiation. Atmospheric noise. Founder lead investigator. Not taking advice to lower the average wideband resonance around 260. Just make a circle out of the antenna 4 inches long, and send the opposite lead to the mic metal mesh, and it lowers the gain to remove interference. vparanormal.com. $1977. That was the year I graduated high school. $60. Whoa. This is vParanormal. Look at my website. Oh, this guy is on vParanormal. No, he only had 2 posts. Robert Veach, lead investigator. This is vparanormal.com. Looks interesting. Show appearances. $2015. I want to try to get through this. A lot of this stuff is years ago. Wait, did I? I'm on the wrong web page. So, let me see if I can get back. Wait a minute. So design considerations for the Raudive diode. Let's just go back over that page. And we calculated 8 kilohertz. There's no coil in there. So here it says Friedrich Jurgis, unofficially credited to 1959 discovery of EVP we know today, etc. Following contacts advice from the other side, Jurgen began to use a radio and settled on a medium wave frequency of 1450 to 1600 kilohertz. circuit Professor Schneider chose was based on an old cat whisker or crystal radio set of the early days. The diode method, a short 6 to 10 centimeters long, 1 centimeter I think is, no, 2.45 centimeters is 1 inch. So that's 4 inches. Is used to give more or less broad-banded signal, which is rectified by a diode and fed directly by cable to the radio or microphone input of a tape recorder. Oh. Oh, now I understand something. It goes back to the premise of the tape recorder. This is not used in live recording. The Raudive diode system was connected to the tape recorder, and then the tape recorder had to be played back in order for you to listen to it. So why even bother using the diode in the first place, because you get EVPs anyway. This screen can be easily manufactured. The old type of diode, OA81, could well be replaced by a more modern one. The screens must be effectively covered and then earthed independently. T and X had great... OA80. This is... This was connected to the input of a tape recorder. There's block diagram 3 over there. This was not used to connect to an earphone. T had success with circuit 3, but circuit 2 is only a blueprint. T uses a commercial 2-stage valve amplifier for shared aerials to which a diode screen is coupled. That's circuit 3. Has this been bookmarked? Yeah, I bookmarked everything, I think. I hope I did. I must have. The following day, Mr. Stanley inspected the diode box and within seconds proclaimed the diode and circuit was ordinary and had no particular value. Oh, wait a minute, I missed something. See, on page X of the preface, the breakthrough, the diode box is described as a small box twice the size of a matchbox with 2 inches of wire sticking out at one end and another smaller wire at the other end, which was to be placed into the input of a tape recorder. That's the big issue right there, the tape recorder. Not understanding diode's function and wondering if this diode was some type of elaborate hoax. He offered to build another diode, but within the hour for the publisher to Tuesday and experience later that evening. Even though there are no valves listed for the parts, the schematic clearly shows the diode circuit had evolved from diagram 1 to which included an untapped double coil and a capacitor. And you see it's connected to this tape recorder. And that was the other circuit. Now see this circuit here, this is way different from the other one. And there's a coil here. It's like a clipping freaking circuit or something. Microphone input jack that connects to a tape recorder, see? That's interesting. That really puts a damper on everything. I thought an earphone was connected. However successful a Raudive diode was, it quickly fell by the wayside in favor of a new device called the goniometer. Five years later, during a trip through Europe, George W. Meek of Spiricom fame obtained the device from Diode and brought it to the U.S. for continued research. After making some necessary repairs, Mr. Meek forwarded the device, etc. My friend Erlen Babcock that I met in Massachusetts met George Meek, so I have indirectly contacted this fellow. The goniometer. Oh, how come that's not showing? Oh, it's just a little slow. And that's the crystal diode, crystal radio. I was thinking I was going to do, there's another section here. I wonder if it talks about the value for that inductor. They got taps, wire taps on that coil. Wire taps. This common circuit did not use a tuning capacitor, but used the capacitance of the antenna to form the tuned circuit with the coil. The capacitance of the antenna. The detector might have been a piece of galena with a whisker wire. So the antenna capacitance. Oh look, the modern crystal radio looks just like someone built that, just like the Raudive diode. Frequency cutoff, integrated circuit, differentiated circuit. Oh, this is the VLF receiver that we were looking at. This one, well, this one's by Inspire. This is a much more complicated circuit. There's some audio amps in there. The final audio amp. It's a 2N222, that's easy. Bypass capacitor. Basic amplifier circuit. That's a filter. See, this is a tuned filter. Well, yeah, tuned filter. That's a bandpass filter, I think. Actually, that might be a low pass filter. There's a capacitor there. There's an FET input. NTE 132. Wow, that's really sensitive. There's some Zener diodes in here. That's your Clipper diodes. I wanted to see if the site was working. Shit. This video zooms into the relic galaxy NGC 1277 near the center of Perseus cluster, over 1,000 galaxies. What? This very rare and old assemblage of stars has remained essentially unchanged for the past 10 billion years. This wayward stellar island provides valuable insights into the origin of evolution of galaxies billions of years ago. This video zooms into the relic galaxy near the center of the Perseus cluster of over 1,000 galaxies, located 250 million light years from Earth. That's what galaxies looked like in the early universe. 10 billion years ago. The universe is like 15 billion. Oh, you can see the red stars around that galaxy. They're circular. Dominated by ancient red globular clusters. This is evidence that it stopped making new stars many billions of years ago compared to 1278, which has more young blue stars. Oh yeah, that's interesting. The blue stars are circular. Oh, that is cool. This is a Hubble Space Telescope image of galaxy NGC 1277. I'll get a little bit off track, but I'm into astronomy too, so. My God, look at all the stars in there. Look at all the galaxies. Oh my God. Are you shitting me? See, I've looked at... Okay, now wait just a second here before I put that picture on there. Alright, so... Oh, crap. If you look right there, where the arrow is, I don't know if you can see that. That's a galaxy there. And there's globular clusters. One near the big... There's that one up there. There's a globular cluster. And that might be Pleiades down there. Oh, I'd love to get my telescope in there. That looks like a galaxy over there. I can just see I can see galaxies like in that picture right there. There's 1, 2, 3, 4. There's a whole cluster of galaxies in there. So we talked about this receiver. I'm not going to get into that. I wanted to get into the user manual. I got all this this stuff. This is a different thing. So we use a shorter wire. There's a nice little receiver right there. So there's antenna capacitance. Sites. Generator tune VL. Did I bookmark this? I might have saved it. Gyrator 1. Gyrator. Yep, I saved that. I want to get into this crystal radio. I said something about a coil connecting to the Raudive diode circuit. Let's see, here they've got earbuds with an audio transformer and a germanium diode. It's all very similar. It's really the same setup except for the fact that it's not tuned. There's a 1N3-4. That's a tuned circuit, see? The classic choice is a germanium diode such as a 1N34 or 1N60. However, germanium diodes are difficult to source these days, so if you can't find a germanium diode, a small Schottky diode like the 1N5817 would also work. At this point, also I would use the diode with the smallest forward voltage drop. There's a 386, a basic 386 setup. Oh, they've got that in that. They got that coil in there, and I got that. Matter of fact, this is the one that I got actually. I just picked this one up. This electronic circuit thing.
Hi, so this is my crystal radio augmented with the LM386 audio amplifier. Now, because the circuit is pretty simple, I didn't make a custom printed circuit board, but instead I did it using my electronic experiment kit, which has most of the components I needed. So on the left-hand side here, I have the tuning circuit, which includes the inductor coil, a variable capacitor here. Then on the right-hand side, so this is the LM386 audio amplifier, which I bought from eBay for just like $1. And that's connected to a speaker here. So this is powered by a 9-volt battery. So in a little bit, I will plug in the battery and then you can hear the sound. There's, by the way, this amplifier circuit also has a potentiometer, which you can use it to adjust the volume. So let me just plug in the battery. So you can hear the sound, hopefully, and then I can tune.
Well, let's get a variable capacitor.
So once I found a channel, I can tweak the potentiometer to increase the volume.
Pretty cute, huh? Eliminating the antenna and ground wires. A TA7642 is a 3-terminal IC shaped like a transistor. It's got some 1.2 battery power. You can buy it EV. I got mine from a jaw-dropping price of 20 Chinese cents, about 3 US cents. Below is a typical circuit. This time the antenna and ground wires were gone, so the circuit becomes portable. You hear the sound through a speaker. You can use the 386 amplifier, etc.
Hi, so this is the improved version of and it doesn't need the antenna, the external antenna and ground wires. So at this point, well, by the way, the circuit is really very simple. It has just the chip and a couple of resistors and capacitors. So at this point, like this piezo buzzer, audio amplifier circuit. So in this case, I've plugged the
Now, there is a possibility, I've heard stories where up in the 50 megahertz band or whatever up there, there's radio signals bouncing around in the atmosphere, and sometimes they've been there for like years, and then all of a sudden they'll end up down, they come down. It's pretty cool. There's that variable capacitor thing. I've got that sucker somewhere. That was my old capacitor. I don't know where that is. Oh, wait a minute. I do know where it is. I do know where that is. That's right on my desk over here. I just found that yesterday. Or today, actually. Let me just grab this little box here. Well, everything gets dragged around. So I got a bunch of little components in that little box. Now this is a little different. It's a tuning capacitor. I don't know how many picofarads that is, but it's air wound. It's a pretty cool little device. You know what? That came off a radio. I think that came off an old portable radio I used to have. I wonder if that sucker's on eBay. And now I'm going to go to eBay. I should put vintage on there. That's an advertisement. That's one of the old ones. That's a walkie-talkie, isn't it? Looks like a walkie-talkie. I used to have an old radio, and I wonder if it's in here. Oh, look at that radio. That radio's in there and I see it. I may end up buying it, but there's some old stuff there. The brown one is close to it. It's supposed to be talking about Raudive design. I'm looking for an old radio. Such is the life of an electronics technician. Was it a GE? Oh, that's close to it. $12. You see what the thing with the old radios, the old equipment, is that they don't have IC circuits in them. They're all built with just transistors. That's a nice looking radio. There's an old radio. What the hell kind of a radio is that? That's a strange looking rig. Pardon my French. There's some old radios there. Well, we'll just do... Ooh, 11 band receiver. I got some stuff downstairs. Oh, that's a nice looking radio. AM, FM, 2 TV channels, VHF. Ah, it covers the ham band. 140 to 174. 144 is the ham band. That's not a radio. That's an amplifier. They're selling that for $20. They think it's a radio? ICF-24. That's an ICF-24. They put the wrong picture in there. That's got to be megahertz. That's shortwave. Probably doesn't have the sideband. Oh, that's a small radio, huh? The other thing I was thinking about, see where this circuit is, this clamper, and it leaves this top portion? That top portion is the voltage across that diode. So what I was actually thinking is what if I could clip the bottom portion and amplify just the voltage across the diode? Would that mean anything? Like, could I take this voltage and do something with it? That voltage is never going to change, though. That's the thing. It was just an idea I had. I just do that in there. It's just too late to do anything with this equipment. I mean, I just don't feel like it. Maybe tomorrow or the next day what we'll do is we'll build. I'm more or less into the design aspects. I was thinking of this this crystal radio. 3D printed crystal radio. That one's got a big ass coil there with thin wires, doesn't it? And an air wound capacitor. Holy crap, really? Where's the diode? Antenna. 19 turns, 45 turns. With some tabs. 260 picofarad variable capacitor. Screw. Oh, there's a diode right there. That's a 47K resistor. Huh! And a crystal earphone. I like this circuit. Capacitor, crystal diode. I saw that picture. There's a battery. Variants of the about radio amateur. What the fuck? How to make a speaker. Steel rod coat hanger, wire tuning slider, 100 to 120 coils of enameled copper wire around a soda bottle, a safety pin, pencil lid strapped to safety pin. Crystal ham radio. Radio di Galena. Huh. That's on that other website I was going to look at. Oh my god, look at that. Sitting on top of that. That is cute. Right there. That is freaking cute. All that stuff sitting on top of the 9-volt battery. It's like art. I could sell that as art and it actually works. You Introduction to Antennas. That's a cute little antenna setup there. Oh, this is a cute little web page. There's that wire wound antenna. It looks like a scalar type. Here they've got a coil around a lead pencil on a razor blade. Crystal radios. Tape loop running. There's some magnetic parts to 4 recording units. What the heck is this? Why doesn't this load up? Tape delay. Why is there a spring on top of that speaker? Oh my god, look at this miniature lathe setup. Holy god. That is freaking pretty. The cutest milling machine ever, but useless. Huh, you can't use it? Huh. E-waste quadcopter using using fans from God. Goodbye. Pinterest always does that. A look at a vinyl record grooves around 1,000 times. You can see the waveforms of the music itself. Battery, voltage to a transformer and a diode to make how to upgrade 5 volts to 500 volts. That's DC 12 volts. There's a timer circuit connected to a transformer. $500-watt 12-volt inverter. Auto voltage, that gets your high voltage. I got one of those downstairs. $5 volts, 220 volts. Look at all the wires on that core. look at their magnets that they got here to rotate this fan, huh? You just put a pen in there with a fan. And chopsticks, whatever, to make a fan with it runs with no energy, with just magnets. That's some interesting crap on here. Pizza volume. This circuit looks interesting. It's a 5-volt regulator plugged into a transformer, and there's just a diode on the other end, like attacking a human. How to use a breadboard. What am I doing? This Pinterest thing is... I don't know what that loop thing is. I'm thinking about doing something with these magnetic heads. There's things about that information. Battery-free loop FM radio. That's a lot of freaking wires. Using a diameter copper tube. There's their version of an antenna that's twisted around this thing here. Getting serious about antennas. I like that antenna. That's interesting. There's a Z match for your amplifier needs. Homemade jet engine plans. .433 megahertz loaded coil. Get out this stupid Pinterest thing. I wanted to get into that one circuit. Wait, did I lose the... I guess I'm done with that Raudive section. Microphone input of radio recorder. See, that's the thing. Okay, I'm building this as a device to measure information directly. However, they're sending this information into a tape recorder, and that negates everything. that I was thinking of doing with this Raudive diode setup. What did I do originally? So originally I wanted to access magnetic information, to transduce magnetic information and listen to that data. See, I don't know why you wouldn't be able to hear this stuff. Why does it have to be plugged into a tape recorder? Raudive receiver modernized. God. Are they selling this? Enabling the device to be used with smartphones and laptops. You can't use that with a smartphone. You can't plug a microphone into a smartphone. An induction sensor antenna which plugs into the smartphone microphone jack. There is no smartphone microphone jack. Not that I know of. Mr. Ghost. Oh, theoretically used for ghost hunting. Huh. He started a Kickstarter to fund his device. He promised to ship Mr. Ghost to anyone who pledged $20 or more. He raised more than $35,000. Oh my God, are you shitting me? But that's an app though. See, he's got an app in there. Did he make the app? The free Mr. Ghost app opens. He probably built that from... Wow. He probably used GitHub or something with free technology or something. I don't know. Who knows? Who cares? What the hell? What else is new? this is connected to a earphone jack. Oh, you connected to the... No, wait a minute. That's just an output jack. I don't think my thing's got a microphone. A simple radio receiver. That one doesn't have a crystal in it. Well, it doesn't have a... Diode detector. What is this rig? Oh, here we go. This is 3819, that's a JFET input. Oh, it's got some good amplification. 1 megohm input, that's your JFET. I don't know what J2 is. Oh, it's another one. All powered by a 9-volt battery. A volume control. That's just an amplifier. Audio amplifier. Development of improved receiver. Input volt 100 microvolts, 600 kilohertz. Oh, what's this one? Sound to work with weak signals from remote transmitting stations. The JFET will amplify over a wide range of frequencies, some up to some hundreds of megahertz. In our design study, the carrier frequency is approximately 1 megahertz, 550 kilohertz to 1.6, in fact, for the medium wave band. As a result, a circuit very similar to that used by the audio amplifier may be used for RF amp. The main difference is that the smaller coupling and bypass capacitors can be used, since the frequency for operation is 100 times high as for audio use. The circuit will tell you the predicted response to a 600 kilohertz signal of 100 microvolts. 600 kilohertz? Ooh. We've got a couple of circuits here we could build. And then we can add the frequencies. Output amplifier. Complete AM radio. The complete receiver. Where's the front end? 2 stages. speaker section. LM386. Wow, this has got everything. The only thing that doesn't have is the filters for the input. Alright, so here's L1 is a call of wire on a ferrite rod. Which means that a circuit has a narrow resonance peak and is better at rejecting unwanted frequencies. Circuit, LC circuit alongside of L1 and VC1, which is used to select or tune the required frequency or station. The inductance used is 729 microhenries, and VC1 can be varied over a range. That means that the range of resonant frequencies is 400 to 1075 kilohertz. VC1 is a variable capacitor. The capacitance can never be reduced to zero, of course, owing to the residual capacitances. Due to the structure, these figures must be added. Any stray or parasitic capacitances arising from the connecting wires, circuit board, and other elements. Diode detector. Diode detector. Transmissions on medium wave frequencies are amplitude modulated. The amplitude of the radio signal as a carrier modulator may rise and fall. Another signal audio frequency of music, the receiver must extract or detect the audio signal, separating it from the carrier. One way to do this is by means of a diode detector. The circuit below represents a diode detector. A PN junction diode. The signal is introduced to capacitor C7. And this is not strictly necessary for the basic crystal receiver, but is included for ease of connection. It blocks the flow of any DC current into the detector. That's not part of that Raudive circuit. The value is chosen as a low reactance at the medium wave frequency of interest, which therefore will pass without hindrance. Very good web page. A simple radio receiver. Files, file list, master, slide images. Oh, I've got that saved. Well, that was interesting. This is the guy that invented it, Constantine Raudive. I wanted to talk about that Abrams guy. Albert Abrams, he's the guy that invented goniometer. Was that what it was? lot of things to... We could play with this stuff, you know? I think that would be the next thing. Just getting the circuits together. I got the capacitor, I got a little coil to play with. I got that picture. All that good stuff. We were supposed to get into that. Student of Carl Jung. Oh, there's not much on here.
And he, along with many others, helped advance the knowledge and technology for spirit communication. After reading Frederick Hergensen's book, Voices from Space, he became fascinated with EVP, and in 1965, he met and started working with Hergensen to record spirit voices, and at first, they didn't really get anything, but over time, they started to hear soft, quiet voices through their reel-to-reel recorder. One night, Raudive heard a series of voices over a recording made earlier that day, and he found out that they were speaking several different languages. He then came up with a device to enhance the quality of EVPs, and that device was the Raudive Diode. He wanted to publish an English version. We're going to go a bit more in depth into the diode, how it works, the schematics behind it. But Konstantin Raudive, I've really been getting into some of his research here lately, and it's very fascinating stuff. So if you haven't checked out his work, his theories, definitely take the time and check them out. And also, there is an MP3 version of Breakthrough that's been uploaded to YouTube. And if you have some spare time, I think it's about 30 minutes long, definitely check that out. It's pretty interesting to hear early theories on EVP, and just different things like that. But thank you all for watching this video, and have a great day.
See, here's the thing right here. Suggested that electronic impulses might be transmitted by the subconscious and impressed on tapes. This is the whole thing about the Raudive diode, was to amplify noise to get this stuff to go on the tape recorder. Why do we have to have the tape recorder? I wonder if it's the magnetic field. What's this here? Hans Bender. What? Hans Bender's the guy I'm looking for. He worked on that other device. John decided soon. Whatever. Annabella Cordoso. Name sounds familiar. This is way back in the day. Field meter, 5 Hz to 400 kilohertz. Connected to UH's laptop in an adjacent room. This is 2009. There's a digital recorder. Audio files, 2 types of noise. Random static noise tuned between 2 radio stations. Huh. They used that same idea from Frank about swapping the radio station noise, retuning the frequency or something. Human speech, either in the form of live conversations or a computer file recorded with human voices. 2008. This is about the time when Frank did his thing. See, because connected to a cassette recorder. Visible speech diagrams. Everybody sits quietly in the chair without moving. Sankowski, that's another name. It's funny, you go to different countries and they only speak German. I mean, they only speak the language of the country that you're doing the test in. That's another key thing. There was that other device. I'm looking for the name of that other device. I thought it was a goniometer. That guy died in '87. Hans Bender. That name sounds awfully familiar. The core of EVP research was confined to the German-speaking countries, which was flourishing. Bender. Okay, this is the guy. What relationship did he have with Uri Geller? Bender would be impressed by the spoon-bending tricks of Uri Geller. There it is, goniometer, right there. Goniometer. I had it spelt right. That's what it is. Parallel. He was an electronics engineer. Theodor Rudolph in Germany, specialized in high frequencies and laser techniques at Telefunken Laboratories. He was also a close collaborator of Mr. Radive and manufactured for him the so-called goniometer. He was the first to investigate, etc., etc., etc. ESP involved in ESP energy as similar to gravitational energy, and experimented with the so-called psychophone. '70s. God, that was almost 50 years ago. Jesus. As for example, experiments with Spiricom, George Meek. same device fails to produce results for another experimenter. My conclusion is that the phenomenon is able to adapt itself to the psychic model preferred by the experimenter. Oh God, wow. This does not mean that the voices come from our unconscious or subconscious, but that our minds are able to formulate a mental intention to communicate that conforms to the particular psychic model that we happen to hold. I think that this mental intention forms the bridge that the communicators have mentioned on several occasions. This bridge allows us to contact other planes of consciousness. Oh, so we're actually talking to ourselves? We're talking to ourselves in other planes of... What if our self is a receiver and we're communicating with us as a receiver? This study is suspended due to lack of participation. Fish harp. Direct writing. What? A direct writing device? This is the skull. Close-up of fish harp, obsidian eye, and spokes. What the hell is this thing? Charles Tart was quoted to argue that EVP is stray radio, and that we who study in this field have not demonstrated the necessary research discipline to produce the kind of credible evidence that he can take to other scientists. The diagram is of a shielded EVP which form an answer touch, projects. It provides more shielding than a metal can or microwave, but is not readily available. We would like to talk to someone who might be able to make one, or who might have one. If possible, we would like to send one to a number of different experimenters in serial fashion so that many examples could be collected in the compartment. Let me know if you can help. Research. This is all seeking examples for study. Study is suspended due to lack of participation. atrans.org. This is the newer. This is summer of 2007. God, this stuff is old. Inverted channel nullification. Method of recording the same sound twice and using one recording to filter noise from the other. Okay, well, oh, like a live. See, I was thinking of doing this. That's just like the laser, isn't it? So if I had two identical setups, but if they both had noise on it, they both would cancel. So one would operate without the antenna. So what we would do, let's look at these pictures. What have I got here? Okay, so what we would do is this. Okay, that's a very good idea, because that was my original plan to do this. If you think about the laser setup, the laser goes to a beam splitter, and then it adds in the end, and so everything that comes from the laser itself goes away, and what's left is your information. So if we have two identical circuits, you could call this, let's see, oh, where's the line? So if we have another one here. This is 10K, and this is 160. And so what we have is this. And the block, we'll put it in this color. This is called a comparator circuit. Out. This would be minus. This is plus. This comes in here. This is going to be red. Do I ground it? No, I can't ground it because that would short this resistor. So what this is, okay, this is the reference circuit. This, they're both identical. This is the input circuit. And this is not the final picture, okay? Maybe we've got all of our amplification, we've got our amplified signals coming through. It's not really in there. Did I have to save that probably? We might have our FET amps and everything all amplifying both sections. Then what we would do, okay, what we would do is put a line through this. We would test both circuits for noise and signal. And that's to calibrate the circuit. And what should happen to that, to both of those signals, is that in the end they should both cancel out. Or yes, the noise on both circuits should cancel. The noise in this case would be the signal itself. Or would it? Wouldn't it be the noise that cancels? I mean, everything's going to cancel. But that's the idea. That would work. I got that idea from here. It says ICN, or inverted channel nullification, recording of the same sound twice using one recording to filter noise from the other. A mono microphone is used to the channel the sound produce a copy of the recording. In results, the copies will be identical, although the majority of the sound cards will be a minor variance, etc. These variances are minor. That's the same with building up two separate circuits, two channels. And in the experience I made, they only show up if you amplify the signal so much you've distorted the original recording enough to make it unusable. In essence, these recordings are identical for the purposes of all but the most stringent investigators. Why is this useful? When two recordings are made of exactly the same sound, they should in theory contain exactly the same data. It should therefore be possible to invert one of these recordings and make it the exact opposite sound wave to what was originally. That's what that diagram was that I just showed you. One of them goes into the plus and the other goes into the minus. That's the inversion. That takes place at the very beginning, and everything after that gets amplified. So all the negative portions and the positive portions are both amplified. If the two sound waves are identical, they should be. The result will be a perfectly flat sound wave because all data in the recording will disappear. In the EVP investigation, sometimes a case two will record at the same time and see we get different results. Well, they got different devices. With the IC and the possible variance are reduced significantly, both recording the same person. This means you should have two copies of the same thing, but we've already mentioned in EVP, recording the same thing twice does not give you the same results. EVP can report out one recording not with the other, and with IC, and there's no difference. Two channels, so there's an advantage. Well, what if you haven't recorded it 4 times? If you have 4 of them? This isn't the only potential advantage. With 2 copies of the same recording, you can use one to filter the background noise from the other. EVP as an investigation is notorious for noisy recordings. In this method, you can rid yourself of that, leaving only the sounds present. Of course, you still live for the test of listening to real recordings. In those cases, on both. As soon as I move it. To perform, all you need is a computer with a stereo sound card and a microphone, blah blah blah, and audio manipulation software to do the inversion. Oh, this does not work. You can't do that. You'd have to have 2. Oh, if you got 2 channels, a right and a left. And then invert it and add the 2 channels. Well, that's the premise of It's an idea. Whether that goes through with direct communication or not, I don't know. Etherical to physical interface. There's another thing, stochastic resonance and earth resonance and that sort of thing. Call for participation. That was 2017. Such as that produced by a fan or running water. The VP is recorded by ambient sound. Radio sweep technology, Frank's box, blah blah. Please pay close attention to examples. EVP maker and devices like Ovilus cannot be used for this study. Frank's box, hacks, and ghost boxes cannot be used for this study, so obviously there's a problem with that. It's okay, but there's noise there. Noise has temperature. Mean effect size versus local site area time for entire data set. It looks like the magnetic field calculator is useful. If you wish to use a smartphone app, there's also a citizen scientist project being conducted by NOAA testing cell phones for geomagnetic measurements. Sidereal clock app. Sidereal clock. There's a lot of stuff here. Probably have to. There's a lot of stuff here. Sounds of presumed biopsychosomatic or can't even read it all. This talks about phonemes, which is sound stuff, dynamic time warping. A seance room, 2010. The Felix Experimental Group. There's a lot of stuff in here. Just bear with me for a second here, Tom Butler.
Did you know the smart
Local magnetic noise sources, like bridges, iron pipes, and other metal objects.
Earth's magnetic field and noise sources everywhere you go and send us the valuable information.
Oh, what's this here? Did you get the image of it? Kinesiology. It's not going to show up. I guess that's it really. I've got all the information I need. I got the diode, I got the filters, I got the fact that we're going to use two circuits to create noise. We've got inversion, we got the preamps, the amplifiers, we got everything that we need to build this stuff. We got it all.